All right, so we're going to be starting our look at distributions of data. And today we're going to be describing location within a distribution. So distribution of data, that's the shape of the data, that's what it looks like, it's what all the data values are. We're going to be talking about where particular values lie and why that might be important as we go forward. So today, in this section, we're going to look at measuring the position using percentiles. We're going to talk about cumulative relative frequency graphs. We're going to talk about z-scores. In the next video, we're going to look at transforming data and defining and describing what a density curve is. So here we are. You should be familiar with percentiles from standardized testing. What we're doing is we're talking about describing the location of a value by what percent of observations are less than it. So the pth percentile is the value with p% less than it. For instance, Jenny has a score of 86 on the test. We have this stem and leaf plot representing the entire class. Her score is right here, 86. What percent is less than her? What is her percentile? So her score is greater than 21 of the other scores. There are 21 red numbers. 21 numbers less than hers. So 21 of the 25, 21 divided by 25, that's 84%. So Jenny is the 84th percentile in her class. One thing to note is that there is no such thing as a 100th percentile. You can't be the 100th percentile because that would mean that 100% of everybody that took the test is less than you. Well, you can't be less than yourself, so that doesn't really make sense. So we don't talk about the 100th percentile. The best you can be is the 99th percentile. A cumulative relative frequency graph is called an ogive. It displays the cumulative relative frequency of each class. So here we have the age when the first 44 presidents were inaugurated. So there were 2 presidents that were between 40 and 44, 7 between 45 and 49, 13 between 50 and 54, and so on. The relative frequency, that's going to be a percent, remember. So we're taking 2 divided by the total. 2 divided by 44 is 4.5%. 7 divided by 44 is 15.9%, and so on and so on. 3 over 44 is 6.8%. The cumulative frequency is different. The cumulative frequency is going to look like this. The cumulative frequency for this first group is 2. The next value is 9. Why is it 9? Well, what we're really looking at this class is less than 49. Less than 54. I'm looking at these numbers here. So this first 2 means that there were 2 presidents less than 44. 9 presidents were less than 49 because it's both of those 2. There are 22 presidents less than 54 because it would be all of those. So we're adding up everything previous to that, and that's where the cumulative frequency is coming from. The cumulative relative frequency, well, we're going to calculate that similar to how we calculated the relative frequency. We're going to take each of these numbers, the cumulative frequencies, and divide by how many we had. And one thing to note, as we go down the cumulative frequency column, the last group should be everything, should be 44. Because everything in our data should be less than the maximum. And our cumulative relative frequency is going to be 100% because, well, it's everything. So here's an ogive. We plot our cumulative relative frequency and our age at inauguration. And we should always see these ogives going up, starting at 0%, ending at 100%. From these graphs, we can talk about percentiles. So we have this graph. We have 2 questions. Was Barack Obama who was inaugurated at age 47, unusually young. So where is 47 on our age axis? Well, 47 is about right there. What's the cumulative relative frequency based on our graph? Well, it's about 11% or 12%, somewhere in there. We're estimating that only 11% of all those presidents were younger than him. He's the 11th percentile. So yes, he was unusually young compared to everybody else. Estimate and interpret the 65th percentile. So we find 65 on our percent scale, right about there. We go directly horizontal to our graph and down to our age, 58. So what does that mean? Well, what it means is that 65% of all the presidents were less than age 58 when they were inaugurated. And conversely, 35% of all presidents were older than 58 when they were inaugurated. And the last thing we're going to look at today in this video is a z-score. And what a z-score does is it tells us how many standard deviations away from the mean we are. It tells us how spread out our data value is. So it also tells us what direction. Are we above the mean, greater than the mean, or less than the mean? So here is how we find our z-score, our standardized value. We take our data value, x, subtract the mean, and divide by the standard deviation. So we're finding out how far apart they are, and then by dividing by standard deviation, we're looking at how many of those we are away. A way we can use it with a little bit tighter notation, x minus x bar, or x minus mu a lot of times, over sigma. Mu and sigma would be for population, or if we're talking for a sample, our formula is that. We can just use mean and standard deviation and not worry, are we dealing with population or sample. So Jenny, back to Jenny, she got that 86 on her test. If we took that set of data and found the mean and the standard deviation, remember we can do that with our one variable statistics feature on our calculator, we get 80 and 6.07. What's her standard score? So we're going to take 86, her score, subtract 80, and then divide by 6.07, and we get 0.99, positive 0.99. That means that she's almost one full standard deviation greater than the mean. And you might think, well, who cares? Well, what we can do is we can use z-scores, use standard scores to compare two individuals in two different distributions. So we have her stats test, the score of 86, and she's got a chemistry test that she scored an 82 on. They're both fairly symmetric. We can find the mean of them both. The mean score on her chemistry test was only 76, and the standard deviation was 4. So a little bit lower scores, tighter packed. Which test did Jenny perform better relative to the rest of her class? We can make this comparison not just by looking at, well, she got an 86, that's a higher score, that's better. We're talking in comparison to her classmates. So we're comparing to the mean using the standard deviation. So here's her z-score for her statistics test, 0.99. Pause the video quick, calculate what the z-score would be for her chem test. So what you should have done is 82 minus 76 divided by 4. And we get a z-score of 1.5. That means she's 1.5 standard deviations above the mean. So she's further away compared to the mean. And because this z-score, this standard score, is higher, that's the test that she did better on relative to the rest of the class. Yes, the grade isn't as high, but relatively speaking, she performed better on that one. And that's where we stop for today. We'll pick up in the next video with those probability distributions.